Hello students, uh, in this lecture we shall study the first chapter of ARM, that is ARM Embedded System and ARM Processor Fundamentals, presented by Hanumant S. Pidashetty, lecturer, Government Polytechnic, Mudhol. So ARM stands for Advanced RISC Machine. So it's a RISC machine, and some improvements have been taken place in this machine. So that's why it's called as advanced RISC machine. It's a RISC architecture, and it is a 32-bit processor, and it is developed by ARM Limited, and nowadays now it has been taken over by NVIDIA. It was introduced in the year 1985, and by 2001, 1 billion ARM processors have been shipped worldwide. That shows its intensity, how ARM is developing. So, let's first learn what is RISC philosophy. So, RISC stands on four major design rules. So, those are instructions, pipeline, registers, and load and store architecture. RISC has got reduced number of instructions, and each instruction can execute in a single cycle, and each instruction is of fixed length. So this improves the user performance, and it also helps in coding much easier. So second philosophy design rule is pipeline. RISC uh, have been designed such that each instruction of fixed length, so thereby it is uh, the processor will fetch an instruction before the first instruction has executed. So this allows much higher throughput. So that speeds up the process. So RISC are very much suitable for pipelining, whereas CISC, since the in the CISC complex instruction are there, so those cannot be brought down into pipeline so easily. So RISC is more suitable for pipeline. The next design rule is the registers. RISC machine have larger number of general purpose register set. So it has got more number of registers than CISC. So general purpose in not the total register, but general purpose registers are more in RISC. So what happens when more number of general purpose registers are there? The data processing instruction can easily store their intermediate results into these registers. That helps in coding much easier. And the last design rule is load and store architecture. So in the RISC machine, there are separate set of load and store instructions are available. So which helps in bringing the data from memory into the register file. So whereas in the CISC, we don't have a separate load and store instructions. So all the data has to be brought from using some specific instructions only. So these are the main design rules that makes RISC so popular. So these are called as the RISC design philosophy. Now, based on this, the ARM has been developed. ARM has got its own speciality. So the ARM has been designed on certain things. So those are called as ARM design philosophy. Now, the first point is battery power. ARM has been designed so small to reduce the power consumption. So it has been designed very small compared to other controllers, so which reduces the power consumption, and in fact it provides more battery life. So this is very much useful in the handheld devices like mobiles or tablets, anything. The second, the quality which uh, popularizes the ARM is high code density. So in the embedded system, the systems are designed such that they are memory constant. That means to say they will have some limited memory. If the code density of a processor is higher, it will have a larger space for storing many files. So that is very helpful in device. That is, and it is a unique quality of that particular embedded device. So here ARM has got a higher code density and which improves the memory storage. So it's very helpful in the device which have limited memory. The third point is price. ARM are price sensitive and they can use low cost memory devices for their development. So this will in turn allow in turn producers or in turn allows to have a lesser cost of that development. So which is an again an attribute to the ARM processor. Fourth point is size. So the ARM processor, the very small area of die is taken for ARM processor development. So in a SoC stands for system on chip. So if the smaller area is taken by the processor, it allows the more peripherals that can be added on that particular chip. It leaves the area for peripherals to be added. So ARM is designed very small, so it can have more specialized peripherals that can be added onto its chip. The fifth point is hardware debug technology. So ARM has incorporated hardware debug technology on its machine, so which allows the engineers to look into the machine what's happening inside it while the system is running. So this feature is very much useful while we are developing any system using ARM. So it allows the engineers to check what is happening and it with which we can debug the machine very easily. So it reduces the prototyping time. So it's very helpful with this feature. Last but not the least, ARM core is not a pure RISC machine. So ARM is takes the advantage of both the RISC machine as well as CISC machine. So that's why it is called as not a pure RISC. So some of the advantages, it takes some of the advantages from CISC machine and some of the advantages from RISC machine. That's why it is called as it's not a pure RISC architecture. So these are the ARM design philosophy. So in the ARM design philosophy, battery power, high potency, price, size, hardware debug technology, and it's not in a pure RISC architecture. So these are the ARM design philosophy. So moving on to next, there is instruction set for embedded system. So there are modifications that took place in the instructions that makes this ARM very special. So ARM instruction set differs from RISC definition in several ways. So these are variable cycle execution. So ARM for certain instruction, for example load and store instruction, it provides variable cycle of execution. So if you in the load and store architecture, there are some instruction called as load multiple register instructions. So during those instructions, so it will load many register at a time from a memory. So when it executing this instruction, it takes number of cycles based on the number of registers present in the instructions. So here, so as I told in the previous slides, that is RISC has got fixed length of instruction. So here that quality is not applicable for ARM, because for certain instructions ARM is taking not fixed length of instruction. So it is taking more than the length of instruction, more cycles than the length of instructions. And the second quality of ARM that differs from RISC is it has got inline barrel shifter. So with this, ARM will pre-process one of the operand before it enters into ALU. So this specialty provides ARM some improvements in the performance. Like, so it pre-process one of the operand. It can multiply or divide the some operands before it enters to ALU. This will provide larger, you can say, it will provide code density as well as the throughput also, because it pre-processes one operand before entering into ALU. That is that increases the speed of operation. Also, within the instruction, you can perform two operations together. That is, while adding, you can perform shift operation as well. So this feature improves code density as well as performance. The third quality of ARM that is different from RISC is 16-bit thumb instruction set. ARM has got 16-bit thumb instruction set. So by this, the ARM can store instruction as a 32-bit instruction or 16-bit instructions. So when it stores the instruction as 16-bit instruction, it improves the code density about 30%. So we shall learn these things in the fourth chapter in detail. And the fourth quality of ARM that's different from RISC is conditional execution. So using this parameter, an instruction is executed only when the condition is satisfied. If the condition is not satisfied, the instruction is just skipped and processor will move further. So with this, you can easily decide on branching. So which again a factor that improves the code density. So without this, it will say an example. A 20 say 10 line code can be reduced to some 4 line codes using this conditional execution. So because it has got a intellectual branching, you can say. And the last quality that differs ARM from RISC is enhanced instructions. So in the ARM, we have got some specialized instructions are added. So like say DSP, digital signal processing instruction. So if you want to calculate FFT, there are instructions available in the ARM, so which are not available in the other RISC machines. So these are the things which makes ARM so special in the RISC family. So next, we shall study an embedded system designed using ARM. So embedded system hardware. So here in this diagram you can see a ARM processor is there, and there are many peripherals and controls are in the total system. So when you see this, so it's just an example how we can design a system using ARM. So in this we can see there are 4 components. One is ARM processor. So ARM processor is the core of that system, which takes the action or which initiates the actions, and there are some controllers, so which coordinates important function block to the processor core. So here in this we can see 2 controllers. There is one is interrupt controller and another one is memory controller. And there are other peripherals. So peripherals are like, so they provide input and output capability to the external to the chip. So from external world, we can have input and output using these peripherals, and these peripherals are uniqueness of particular system. So that means to say, not all the system will have the same set of peripherals. The last one, that is bus. So here there are buses used for communicating different connecting different blocks and used for communicating the information from processor to peripherals. So this is how an embedded system looks like. The embedded system, which is designed using ARM, has got an ARM processor inside it. Now let us study ARM bus technology. So usually in your system, there is a bus called as PCI bus, peripheral component interconnect bus. So using that bus, you can add many features, peripherals onto that bus. So like that, there is a bus designed on chip, in the ARM chip. So that we can call it as ARM bus technology. And here normally there are two different types of devices that are attached to this bus. So those bus devices can be categorized as bus master and bus slaves. So bus masters are the one which initiates the data transfer, while bus slaves can be termed as the device which just responds to a request. So here in the previous system, so here our processor can be taken as a bus master, and all other peripherals can be treated as bus slaves. Now, while designing a bus for any system, so we should take two architecture level into consideration. One is physical level, another one is protocol level. So, in the physical level, we mainly deal with the electrical characteristics of bus and some bus width. So that means to say how much power it is carrying or how much voltage it is withstanding. All those things can be dealt in physical level, and bus width, that is say 16 bit, 32 bit, like that. So what is the bus width? So those all things are taken care in the physical level. And in the protocol level, so it protocol level governs these are the set of rules that governs the communication. I mean to say, uh, which device has to communicate first, which device has to communicate next. These are the things taken care by protocol level. So ARM has come up with one bus called as AMBA bus. So AMBA stands for Advanced Microcontroller Bus Architecture. So this was introduced in the year 1992. Initially, the ARM introduced two buses, that is ARM system bus and ARM peripheral bus. And later on, they came up with another bus called as ARM high performance bus. So this AMBA bus, with this we can have a plug and play feature. So plug and play feature means, so any peripheral can simply be bolted onto that bus without having to redesign it. So with this feature, we can just put any peripheral onto the bus. You need not to design whole thing. So that is the plug and play feature. So this is very helpful whenever an engineer wants to design his system. He need not to worry about this bus architecture. So he has to just place his peripherals onto this bus. That's makes again easy to market or easy to prototyping. Now AXB bus is a centralized multiplex bus, and it has got a higher throughput than the ASB bus. ASB bus is a bidirectional bus, and ASB runs at higher clock speed, and it supports 64 to 128 bits. ARM has introduced two variants of ASB bus. So those are, one is multi-layer ASB and another one is ASB Lite. In the multi-layer ASB, ARM allows to have more than one bus masters. Bus master, I already told what is bus master. That is the device which is capable of initiating a transfer are called bus masters. So with the multi-layer ASB, you can have you can have multiple bus masters active at a time. So that allows the co-processing to be added into your system. Another variant of ASB, which is called as ASB Lite. So it is a subset of ASB. That means to say, this bus will have only small features or certain features of ASB, not all. So, and this is limited to a single bus master. So these are two variants of ASB bus available in the ARM: multi-layer ASB and ASB Lite. So next, let us study the peripherals. So I already told that peripherals, the device which improves the input and output functionality of a device off chip. So that means to say, the processor has designed, the system processor core has been designed, and these peripherals provides input and output capability to this particular processors. And usually each peripheral performs a single function, and all the peripherals of ARM are memory mapped. That means to say, each peripheral has got some memory assigned to it, so wherein it will store all its data. So it will have its registers, so those registers are situated in the memory, so that's why it is called as a memory mapped peripherals. So it will store all its data onto that memory. There are some specialized peripherals called as controllers, so which implement higher levels of functionality. So like, for example, memory controllers and interrupt controllers. So controllers are again peripherals, but they do some special functions. So memory controllers will manage the memories, and interrupt controller will manage the interrupts. So these two are a special functionality. That's why they are called as controllers. Now we have seen a memory controller in the hardware system designed by the ARM. So here in this slide we are seeing a memory controller and an interrupt controller. So here with the memory controller, we have connected many memories to the system, and interrupt controller is taking care of all the interrupts that are arise in the system or from external source also. So memory controllers, these memory controllers connect different types of memories to the system. So here some memories require configuration on turn up, power up. So for example, some initialization code is stored in some memories. Those memories has to be configured once we power on the system. When once we turn on the system, these memories also has to be configured, because initialization code will be there in that memories. So that those initialization code has to be run before the operating system takes over control of that particular system, because once the initialization is done, then only the OS takes over. And in some memories require some software setup. For example, DRAM. So here in the DRAM, the memory, if you don't refresh the memories, the content of that memory will be lost. So we need to set that refresher rate in the DRAM. So this requires some software setup. So some memories require some software setup, and in some memories it requires configuration on power up. So once you turn on the system, you have to configure that memory because initialization code has to run. So memory controllers that connect different memories to the system. One more important controller in the ARM is interrupt controller. So whenever a device or in a peripheral requires attention of the processor, it will raise an interrupt. So these interrupts has to be serviced. So processor, what it does, it stops whatever it is doing and it will service the requests. Now to handle these interrupts, we have a specialized peripheral called as interrupt controllers. Normally there are two types of interrupt controllers available. One is standard interrupt controller, another one is vector interrupt controller. In the standard interrupt controller, the interrupt controller sends an interrupt signal to the processor. Sorry, it sends an interrupt signal to the processor core, and in the standard interrupt controller, it can be programmed such that it can either mask or ignore that particular interrupt. And usually, each interrupt has got its own interrupt handler. So, interrupt handler means it's a sort of a software program written to handle these functions. So, those are called as interrupt handler. So, interrupt handler reads a bitmap register that is there in the standard interrupt controller. So standard interrupt controller will have some a register, and each bit of that particular register is corresponding to particular interrupt. So this interrupt handler, what it does is it reads that register and checks whether any pending interrupt request is there. So that register, you can call it as a bitmap register, and interrupt handler will read that bitmap register and decide which interrupt has to be executed. There is one more type of interrupt controller called as vector interrupt controller. So this is some specialized interrupt control than standard interrupt controller, because it assigns the priorities to the interrupts. So the processor is interrupted only when the new interrupt has higher priority than the currently executing interrupt. So otherwise, if it is lower priority, it is just ignored. The handler addresses with each interrupt. So for every interrupt, there is a interrupt handler addresses. So those are stored in the VIC, that is vector interrupt controller. And depending on the type of the interrupt, so VIC, it will either call the SIC, that is standard interrupt controller, to handle this interrupt, or it can directly jump to the handler for execution. So in the SIC, that is standard interrupt controller, we don't have any priority. In the vector interrupt controller, we have a scheme called as priority. So based on the priority, it interrupts the processor. If the higher priority interrupt comes, then it will interrupt the processor. If the lower priority interrupt comes, so it just ignores that interrupt. And upon occurrence, or upon the interrupt occurrence, it calls the SIC, that is standard interrupt controller exception handler, and loads the handler address to that handler, or you can directly jump to that handler also. So now, embedded system software. So usually in an embedded system, there are four types of softwares available. So those are device drivers, initialization, operating system, and application software. So initialization codes are, so these are the first instruction that runs on our system. So whenever I already told, there is some memory requires configuration while power on. So when you turn on, So it has to be configured, it will execute certain amount of code. So that code you can call it as an initialization code. And these initialization code is specific to specific particular target. So that means to say, if I have an say laptop, it has got some specific initialization code. Say if it is the make of HP, it will have a different code. If it is a make of Dell, it will have different initialization code. So it's specific to the target. So depending on the machine, it will have different initialization code. And what it does, initialization code, it sets up minimal parts on the board before handling control to the OS. That means to say, so it prepares the system before OS starts. So it just checks whether all the components are working fine or not, and then it will hand over the control to the OS. Operating system, it's like a manager. So it's an infrastructure to control the application and as well as hardware. Applications means softwares. So it's just an infrastructure which controls all the applications as well as hardwares. Hardwares are the machine, hardware machine, that is say maybe keyboard, mouse. So these are all hardware components, and applications are some say MS Office or any other applications. So operating system takes control of all these things. So many a system do not require full operating system. Certain system have got some just scheduler. Scheduler means so which tells what to be executed next. So the total functionality is divided into some tasks. So it just schedule the next task one after other. So many systems do not require a complete operating system like Windows. They just have some scheduler. They just with the help of scheduler they are functioning. The next type of software is device drivers. So these device drivers provides a constant software interface to the peripherals. Say I have a system, a laptop or anything. So if the device drivers are not there, so my microphone or an USB will not work. So with the help of device drivers, the processor core can interact with the peripherals. So they will provide some software interface. So they act like a bridge. So they act between these processor as well as the peripherals. And the last component of software, that is application software. So these are designed for specific application. Say they perform a required task of device. So they are, for example, a diary application in a system or a calendar. So these are they are not actually required for system execution, but they help for the user. They got some particular functionality. They help the user to manage his data. So there are four types of software components available in the embedded system. Now let us list out some of the applications of ARM processor. So ARM processor finds vast usage in many segments. So like say we have networking applications like home gateways, DSL modems, Ethernet 2.11 wireless components. So in all these we have a ARM processors. And handheld devices like mobiles, tablets, other things, they also include ARM processor. ARM processor can also be used in the mass storage device like hard drivers. They can also be used in the inkjet printers, imaging products like inkjet printers. So, and many more applications are there. You may be just owning one ARM system you may not be aware of. Say your mobile may be made of an ARM processor also. So the ARM has got a very vast application.